Hey kids, ready to do linear combinations of sine and cosine? Huh? Wait, what does that even mean? Linear combinations. Linear, meaning I don't have any squares, cubes, or whatever, and I am combining cosines and sines. That is a linear combination, and I want to be able to turn my linear combination into one expression in terms of cosine. That's my goal of today. Before we get there, though, I want to remind you of what we've put in your tool bag so far. When we ask you to prove trig identities or solve trig equations, the tools that you have been taught in AAF and then reviewed in pre-cal was to simplify and be able to evaluate exactly when needed to in order to solve and prove. So what are the tools that we've put in your bag so far? Pythagorean identities, in the bag. Reciprocal identities, in the bag. Even odd identities, in the bag. Cofunction identities, in the bag. We went over all of those and we did some solving and proving and we did a quiz, right? Good job. After the quiz, we gave you some more tools. Sum and difference identities, in the bag. Double angle identities, in the bag. Half angle identities, in the bag. Power reducing identities, in the bag. There's one more tool to help you solve and prove trig equations, trig identities. And that one more to put in your bag is linear combinations of sine and cosine, being able to rewrite a linear combination as just cosine. And you might ask, well, if you have sine and cosine, why'd you pick cosine? Hopefully that'll be a little obvious, but I want you to think about whenever you did modeling problems and you were given right information and you could draw a graph, which graph was easiest to come up with the equation of? So I want you to remember from Algebra 1, you've been dealing with linear combinations for a long time, right? It is just, linear combinations just means you have two things that are to the first power and you are putting them together. 3 of one thing plus 4 of another thing. That is a linear combination of x and y. I'm just taking this x and saying, well, actually, x is now cosine of theta, and y is now sine of theta. So it is just a linear combination of cosine and sine. My goal is to write, not an equation, an expression with only cosine. And again, you might think, why? Think about where we're going. To solve trig equations or prove trig identities. Being able to take two, right? Sometimes I try to factor to get terms into one, right? What if factoring doesn't work? Here is a way to get a cosine and sine on one side of an equation with only cosine. So if you have your calculator, it would be awesome to get your calculator. And I want to show you the graph of 3 cosine theta and 4 sine theta. Here are the two separate graphs. Hopefully, I don't want you to put that in your calculator. What I want you to put into Y1 is the linear combination. I want you to put this in your calculator. But before you do, I want you to think about, this is certainly 3 cosine theta with a sinusoidal axis at 0 and an amplitude of 3, no phase shift. Here is 4 sine theta with an amplitude of 4, no phase shift. Both of them go from 0 to 2 pi. Now I want you to think about putting them together. What you're doing is taking these two equations and adding their ranges. That's what adding function 1 and function 2 is, right? We did that in AAF too, right? I can take two functions and I can add them, subtract them, multiply them, divide them, compose them. I'm taking two functions and adding them, which means you're adding their ranges. Remember, the domain of these are all real numbers. I'm showing the domain from 0 to 2 pi. So you're going to take, for instance, at theta equals 0, you're going to add the new equation that you have in y1. The new equation at 0 will not be 0 and will not be 3. It'll be 0 plus 3, right? You're going to take all the range values and add them together to generate a new one. So if you put this into y1, you should see my purple graph. If you make your window go from 0 to 2 pi and make sure you're in radians, you will see my purple graph. That's what 3 cosine theta plus 4 sine theta looks like. Notice that at 0, the range value is the combination of 0 and 3, which is still 3. But here, the range value of the purple is twice this range value, right? Because cosine theta and sine theta are equal there. 2 times this value is where my purple graph is. Notice that here, where my purple graph has an x-intercept, the range value of sine, 4 sine theta, and the range value of 3 cosine theta balance one another out. And that's why my purple graph is 0, right? And I can do that analysis all along this graph. So my goal, which is an objective we did in AAF and reviewed last unit, is to, given this purple graph, give me an equation. What's the amplitude, period, phase shift, and sinusoidal axis? But I want you to keep in mind where this came from. It's not a modeling equation, right? This came from three cosine theta plus 4 sine theta. That's where my purple graph came from. That's what you have in y1. Notice what has not changed. The sinusoidal axis has not changed, has it? Ooh, the sinusoidal axis is an equation. Theta equals 0 or y equals 0. Oops, y theta? Y equals 0. What else has not changed of these 4 things? Sinusoidal axis hasn't changed. What else? The period has not changed, right? 2 pi. But the amplitude did change. What's the amplitude? Well, my old amplitude was 3 of 3 and then I also had an amplitude of 4. So is my new amplitude just the sum of 3 and 4? Is my new amplitude 7? No. What is your new amplitude? 5? Hey, what do you know? What have you done before that relates 3, 4, and you get a 5? Yep, Pythagoras. Yes, the proof of this, Pythagoras is in it. Oh my, yes, come on in, Pythagoras. Pythagoras is how I get my new amplitude from my 2 old amplitudes. OMG. Now, what about my phase shift? Is the phase shift? Now, phase shift depends upon what I want to write. What was my goal? I want to write a cosine equation for this. I have the period, I have the sinusoidal axis, I have the amplitude. Where is the phase shift if I want, my goal is to draw a cosine graph, right? If I focus on this x-intercept, that's a phase shift if I want to write a sine. I don't want to write a sine, I want to write a cosine. What's the phase shift? There it is, right? This point is where it is. How can I find this distance from the x-axis? Because that's what I want, right? There's my phase shift right there. How far from the y-axis do you start your cosine graph? How can I get that? Well, so far, I have A. I just need my phase shift. Well, check this out. 3 cosine theta plus 4 sine theta is equal to this expression. That's where we're trying to go. I filled in my amplitude. Do you see what I did here? Old news, right? This is the cosine of a difference formula. The cosine of a difference can be rewritten as a sum, where it's cosine, cosine, sine, sine. I use my sum difference here. Now notice that I've got a cosine on the left. Nope, I have an equal sign. 3 cosine theta plus 4 sine theta. All I've done is distribute the 5 here, and I've highlighted cosine theta red and sine theta in blue to match here. Now I need you to look at this equal sign. If 3 cosine theta plus 4 sine theta is indeed equal to what's on the right side, what must be true? This is the law of equality. Those pieces must be equal, right? So 3 must be equal to 5 cosine theta. Do you see that? 3 cosine theta is equal to 5 cosine C cosine theta. So it must be true that 3 and 5 cosine theta are the same. If 4 sine theta is equal to 5 sine C sine theta, there's your sine theta. So it must be true because of the equality. 5 sine C must be equal to 4. Which means cosine C is 3 over 5, and sine C is 4 over 5, which means tangent of C is either positive 4 over positive 3, is positive 4 over positive 3, right? Because the 4 and the 3 were both positive. So I say to myself, self, how do I get C by itself? I take the inverse tangent. What angle has a tangent of 4/3 in quadrant 1? How do I know quadrant 1? Because both y and x were positive, right? Sine is y over the radius, cosine is x over the radius. Tangent is y over x. Positive y, positive x, I must be in quadrant 1. That's how I get my phase shift. Now that was not a special angle. Who has a tangent of, right, 4 over 3? So I just used my calculator. Rounded to 3 places past the decimal. And now in y2, this you had in y1. In y2, I want you to do this. Now, because this is a rounded value, you might see a slight difference. But when you graph y1 and y2, oh snap, they are the same. Whoa, that is so cool. So in y1, that's my purple graph. In y2, here's my graph in black. They are the same. Whoa. So I now have one more tool in the bag. Linear combo of sine and cosine lets you collapse an expression with a sum into one term. So the linear combination of A cosine theta plus B sine theta can be written as a single cosine function with a phase shift of C and an amplitude of A. And how you find A is Pythagoras, and how you find C is inverse tangent. Be careful. The sign of your A and B will tell you what quadrant you are in. A should be written as an exact value as possible, right? I don't want approximations. I don't want you to take the square root of 2 and give me an approximation. I want the square root of 2. However, C, you can round to 3 places past the decimal. Unless it's an exact value, like a speed trig value. So let's do an example. First, make sure you copy down these directions, this word in the direction. Express. You're not solving yet. All you're doing is practicing how to express. I want you to take a sum and I want you to collapse a sum into a single cosine expression with a phase shift. So the dilation factor comes from Pythagoras, right? I didn't copy down the negative because I'm squaring. So 10 squared plus 10 squared is 10 root 2. Please don't give me a decimal approximation. If you said the square root of 200, I'd be like, I'd kind of eye roll you, but that's fine too. C is the inverse tangent of, now I cared about the signs. Why did I care? What quadrant is y positive but x negative? So what angle has a tangent of -1 in quadrant 2? 3 pi over 4. Because this is a special angle, I do not want an approximation. You're supposed to recognize your special angles. That's what speed trig is for. So these two expressions are the same. If you were to graph -10 cosine theta and +10 plus +10 sine theta, if you put that in y1 and this in y2, you will get exactly the same graph. Why this is helpful? When I want to solve an equation and I can't, right? There's nothing to do with this, right? Maybe to try to collapse it, I can use my linear combination and I have cosine by itself. So let's do an example like that. Oh, this was my, right? Put this in y1, y2, and look at it. In these directions, make sure to highlight the word solve. And I am only solving on 0 to 2 pi, so one trip around our unit circle instead of spinning. This time, I have an equation. So I highlighted my sine and my cosine. A, again, don't care about the negative because I'm going to end up squaring. Using Pythagoras, square A, square B, add them together. Square root of 13 is my amplitude. And I always want my amplitude to be, right, positive because I'm writing a cosine graph with a sine. I'm sorry, a cosine graph with a positive amplitude and a phase shift. So here I go, inverse tangent. Be careful who's with your sine, right? +2 is with sine, -3 is with cosine. I keep, because who has a positive y and a negative x? Quadrant 2. So this is where you stop when you are just practicing expressing. But I am now in, so I used, right? I reached into my tool bag and I got out linear combinations because my goal was to solve. So step 1, I went to the tool bag and I pulled out, oh, I can rewrite sine and cosine as just sine. Now I'm going back to, okay, now I got to use, now I'm down to solve, right? I've used my tools. I'm down to solve. How do I solve this? Start to isolate cosine. Divide by both sides by root 13. Inverse cosine. Both sides. Why do I have this? Because the inverse cosine, right, might be in which quadrants, right? I know, remember, now this is different. If I just asked you to evaluate inverse cosine, you are restricted to quadrants 1 and 2. But I'm not asking you to evaluate inverse cosine. You are using inverse cosine to solve for the x that you can put in here and get you 0 and on the, where as long as x is between 0 and 2 pi. So what about these numbers? Are these numbers between, right? What is 2 pi? 2 pi is approximately 6.28-ish, right? So I got 3.8-ish and 1.2-ish. Where's 1.2? And where's 3.8, right? Which quadrants are those in? So now if you want to check your work, go back to the very beginning. The very beginning of this problem was solve you had a sine and a cosine. You had, I gotta flip my notes here. What was my sine? I guess I could go back a screen, couldn't I? 2 sine x minus 3 cosine x is equal to 1. Put this x and this x in here. Now again, you're using rounded values, so you probably won't get exactly 1. But if you stored all of these values, if you stored this, right, all the decimal places, and you put it, you would get 1 if you want to verify. But you're going to get close. Right? Now think about pi. This is pi over 2, right? Pi over 2 is approximately 3.14-ish divided by 2. So that's approximately 1.5-ish. So this is in quadrant 1. My first x is in quadrant 1. What about 3.4? Well, pi is 3.14. Three pi over 2 is going to be 3 times 1.5-ish. So where's this? Right, in somewhere in between here. So you've got a quadrant 1 and a quadrant 3 answer when you put in here to get 1. Okay? We'll do more examples, and we've given you for your practice homework, we've given you a handout to practice these, where you go through solving, and let me make sure. You're given 5 equations where you are just practicing your transformation from a linear combination of sine and cosine into just one expression with cosine. That's the first 5. And then the next ones, then you have 3 where you're actually solving. And I mixed it up, right? Where one of the, sometimes you're doing 0 to 2 pi, sometimes you're doing 0 to 360. Okay, we will see you in your next live session.